In this video, we're just going to recap what we mean by eigenvalues and eigenvectors of a matrix and look at a further simple example. So to begin with, let me remind you of the definition of eigenvalues and eigenvectors. So if you have a square matrix A, say which is n by n, then the eigenvalues of A are called lambda and are scalars, with associated eigenvectors x, which have to be non-zero, and they satisfy the property that Ax is equal to lambda x. And in general, for an n by n matrix, there are n eigenvalues, and each one in general has a eigenvector associated with it. If the eigenvalues are repeated, then one often struggles, cannot find the same number of eigenvectors for a repeated eigenvalue. So if there are eigenvalues, say 1 and 1, which are repeated, one does not necessarily find two different eigenvalues for that eigenvectors for that eigenvalue. But on rearrangement, this set of linear equations for x and eigenvalues lambda can be rewritten in this form, and because x has to be non-zero, then this matrix here must be singular, cannot have an inverse. Its determinant must be 0. And this expression, when multiplied out, corresponds to a polynomial equation of degree n for eigenvalues lambda. It's called the characteristic polynomial, and phi of lambda equal to 0 is called the characteristic equation. So if we turn to the notes, which, if we briefly look at the original set of notes, you'll see can be found the example that I'm looking at now can be found here in example here, which is the one we looked at last time, and following that, example 6.7b. So let's just refresh our memory about 6.7a. We were looking at the eigenvalues and eigenvectors for the 2 by 2 identity matrix, and we found here that the eigenvalues were repeated. They were 1 and 1, but we found two different eigenvectors for that repeated eigenvalue. We're now going to look at example 6.7b, which has similar but not identical properties. So turning to 6.7b, we see here that the matrix A under consideration is similar but not identical to the identity matrix we looked at before. So the previous matrix in example 6.7a was this, and so we've altered this 1, 2 element to be 1. If we then form the characteristic equation as the determinant of A minus lambda I, then again we find this becomes a quadratic equation, which is identical to the quadratic equation for this example here, because that was the determinant of 1 minus lambda 0, 0, 1 minus lambda being 0. And if you multiply out the left hand side, you get 1 minus lambda squared. What you will find is this is an unhelpful property of a iPad, that if one leans on the right hand side it jumps. But anyway, what we know is that, at least with this iPad, we can do nice things like this and even change the colour. In this case, if you multiply out the determinant, you find this is equal to 0. So the same thing happens if one forms the characteristic equation, even with this number now being 1 and not, as it was previously, 0. So you still have repeated eigenvalues, but in this case, if we look for the eigenvector associated with that single repeated eigenvalue, then this time the set of linear equations, which is for one's eigenvector x1, forces the second component, as we'll see by multiplying this out, y1 equal to 0. So previously above, we had no such constraints. The set of linear equations for the components of the eigenvectors corresponding to the eigenvalues 1 and 1 were automatically going to satisfy the set of linear equations regardless of their values. So that gives us 2 degrees of freedom and hence 2 linearly independent eigenvectors. However, in this case, for this slightly modified matrix, the second component must be 0, and that only leaves us with 1 degree of freedom, that x1 is not prescribed, so that can be any value t, say, which has to be non-zero, so we end up with a non-zero eigenvector, but we only get 1 linearly independent eigenvector for that eigenvalue, which is now repeated. Now later on we'll look at cases where we have repeated eigenvalues with a complete set of eigenvectors and others where we do not have that. So let's just have a look at what Wolfram alpha does for this problem and see whether it replicates what we've just seen. So if I turn to the notes, which are here, you'll see that the Wolfram alpha link is given, and it will compute, as shown here, the eigenvalues of the matrix I've just described, 1, 1, 0, 1. So let's just click the link and view the page. And this is what we find. And so either typing that in or having clicked the link, pressing return, we'll see that the eigenvalues are repeated. As shown, they're just 1 and only 1 corresponding eigenvector. Let us just note that if we change this to be the previous example with 0 in here, then we get, as expected, 2 eigenvalues which are repeated, but 2 linearly independent eigenvectors. Let us again return to the notes and look at what, in this case, octave gives us. So this is the octave online command, again to work out the eigenvalues and eigenvectors for that same matrix. So I'll just copy that, and this is the link to Octave Online. We'll move to the web page view, and if I type that command in, put that command in here, then that should work out the eigenvalues and eigenvectors for this same matrix. V will be the matrix of eigenvectors and D the eigenvalues. And there we have the eigenvalues on the diagonal of D, 1, 1 repeated, and then in this case we have what would seem to be two eigenvectors, 1, 0, minus 1, 0, but of course the second one is not linearly independent from the first one, it's just minus the first one, so it's not a new value. So in the next video we'll be looking at more general cases of repeated eigenvalues and whether we have a complete set of linearly independent eigenvectors.